Anyways, now let's get started on the load part of it. And the load part won't be as hard as the saving part, because we did most of the work, right? So we're going to create a function, another public function. Public static void. Actually, not void, because we're going to return the neat genome. We're going to copy all the information over into a neat genome and return it, and that will take the place of the genome in the network. Okay, so neat genome. We're going to call it load network. Load genome. There we go. And we don't pass it anything. We just use this to return. Okay, now over here, we're going to get that file and convert it to a string. So string, save string. Actually, we'll call this genome string equals file dot read all text. Same thing that we have up there, the data path plus the name of. Now this has to match what you have over here. You can add a different system, whatever you want, but for the way that I have it set up, these have to match. You can like pass your own names and stuff, have different names for the files. I don't see the point in that, because if I want to save this, I'll just rename this to something else. And the next time it will run fresh. And the next file will be called save.txt, but I'll still have the renamed file. So it's going to be save.txt, has to match the top. And that should be good to go. That'll read the file. Let's do a console.log to make sure. That shouldn't be console.log, it should be print. Oh yeah. So, and then this has to return. For right now, no, I'm going to have to write this. It's going to be, it's not really going to let me debug properly. Alright, that's fine. We'll write the whole function and then we'll do the debugging of it, because I'm pretty sure this gets the string. So then we have to take that string and convert that into a genome JSON object, which is our serializable save genome, the serializable JSON genome class. And then this will be JSON utility dot from JSON genome. We pass in that genome, and since it's a serializable class, it's already mapped. Oh, it's made to be mapped. Save string. Nope. This is genome string. Yes. Alright, so this function right here will take your genome string text and convert it to the genome JSON object. And this is going to be your genome JSON object. And now we have to copy that over into a genome. And for that, we have to create a genome. That will be genome loaded genome equals new genome, and then for each So basically for each node gene JSON that is in the saved genome, so it's the opposite of what we did in the save. Alright, so we loop through the genome JSON object, and we simply gene new node. We create the node gene, which should be initialized, and we could just use the initializer here to set our stuff. So save node.id, we pass it in for, let me see if this will work. Hold on, tooltip. Oh, this has to be capital N. Alright, let's just go to our neat genome. Our node gene is right here, and our first one is the ID, our second one is the type. So that's what we'll pass it from the saved node. And we pass in save node.id, and we pass in save node.type. Right. Type right here. I wonder why this is not colored right. Probably something I'm doing wrong, but we'll see. So let me say the type, but the problem is we need to cast it to the proper type, because node gene JSON type won't automatically convert to node gene type. So we have to just do node gene dot, oh, that's capital N, node gene, so that class type, and that should cast it proper. Now let's close that up, and that fixed the coloring good. And let's move on. Now that those are created, we just add it. So loaded gene dot add this will be loaded genome. Let me go to my genome real quick. Dot node genes dot add, and we just add the new node. There we go. And then after that, we do the same thing for the connection genes. Now we'll create a new con gene. And we just pass in all the information same way. That'll be saved con dot input node, saved con dot output node, saved con dot wait, saved con dot is active, and saved con dot innovation number, which is enov number. Enov number, there we go. Perfect, and then we add that. And there's our genome completely populated, and now we simply return it. there's our load function done. Now, but how do we know it's working? You know, and I agree with you, that's a valid problem. Let's figure it out. So now we're going to change the way our new genetic manager is working. And this is why I kind of wanted to have this in a different video, but I'm not sure. Now, we want, basically, if we're going to have a bool that says that spawn from best, or whatever, spawn from load. And when it's true, all of our networks will be spawned from the best network. And if it's false, we start fresh. Every brain is starting with no connections and just one mutation. So first we have to create a system to save the best, and then we can create a system for loading the best. So let's get started on that. And once this is done, that will be the end of the loading and saving. But we're not done yet. Let's finish it up. Hang in there, you guys. I know this is a long one. I appreciate you guys hanging in there. I might actually break it up though. Okay, now let's set up the genetic manager in a way that is actually able to get the best networks and is able to load the best networks. And to do that, we're first going to add a bool, a public bool. We're going to call this spawn from save. Let's just keep the convention. I'm going to set it to false. Okay? Alright. Now we're going to add a if spawn from save equals true, then we're going to do something. We're going to spawn from the best, and if it doesn't equal true, we'll just start the networks like we normally do. Because our starting network function is what generates all of the initial our initial genomes. So now up here in our if statement, we're going to do, the function is going to be called starting best networks. Okay, because this is going to be the function that starts from our save. But I think a better one, starting save networks. Not networks, network, because we're going to have just one save file. From one genome, all of them will be populated. So now let's scroll down to our starting network function. Right here. This is where we spawn the new neat networks, right? But we don't want to do that for the other ones. I know I said I don't want to copy and paste a lot, but that's just a lot of work. Whatever. Okay. I just Control Z to put a copy and paste it. I'll just write it. Starting save network, and we'll write the function for it. Okay. Now we're going to do for int I, and let me just make sure I want this part to match my source code. All right. From saved network. Okay. Oh no. I'll write that right here. There we go. And now, so we want int basically the same loop we have over there, up on top, right here. I equals 0, I is less than starting population, I plus plus, we're just looping through up to our starting population. So in our case, 20 from 0 to 19, that's what's going to be printed. And now that's done, we're going to do all neat networks, and we might have to add another way to initialize real quick, but all neat networks I equals new neat network. And now over here we pass in how many input, output, and hidden nodes we want to have. But here, since we already have all our information, we just want to pass in the loaded genome. So we do that by calling neat utilities.load genome, that function we wrote. So this function will pass in the loaded genome to our network in the constructor, and so our network will now have it built from this. But let's go to our neat network and set up a constructor to work with it being passed in a genome instead of input nodes, output nodes, and hidden nodes. So open up your neat network file, and let's take a look. So right here we have one constructor that takes in 3 integers, but we need another constructor that takes in a neat genome, because we're passing it an already created neat genome, and we simply want to we're already passing it a created genome, and we simply want it to create the input nodes, output nodes, and hidden nodes off that genome instead of off of the list. So let me open that up in my source code as well. Alright, so our other constructor will look like this. Public neat network genome, neat network, neat genome, and we're going to set up our genome from there. So my genome equals genome, that the genome that's being passed, and then we simply copy over this information here. So the only difference is we don't need to create initial genome. Cool. I'm not going to type all that. That's way too much typing for me. I'm going to copy this up here and paste that right there. And that should be good. And we need to just create the network. And then this should work. Okay, I will be right back. All right, I'm back, and we're going to continue this up and finish it up. Okay, so right now, let's scroll up to the top, and we have our spawn from save set up. So if it's equal to true, it will start from the starting save networks. And if it's not, then it will just start networks normally. So let me make sure that name is proper. Yep, save name. Alright, let's see if this is working fine. So we're going to open this up, and it seems there's an issue. So anywhere I have just genome JSON written, it should be neat genome JSON. So let's go ahead and change that. And so just in these two places, change that from genome JSON to neat genome JSON. Let's go ahead and save. Okay, let me see what line the error's on. 41. Right here. There should be no gene. There we go. Save that. And that is perfect. Fixed our issues. And now let's go to our gene manager. And we already have a save, right? Our save is right here. You can see it. So since we already have a save, you can see all the information in there too. When we click play, it should open. From all of them should be moving in a unique way. They shouldn't be like, not unique as in they should be unique from each other. They should all be moving similar to each other, but not just in straight lines like we have usually. You should see that there is a network being spawned from some complex brain. So we'll go to genetic manager and spawn from save. We'll put that to true and press play. And you see now they all kind of move similar, but it's complex behavior because it is being, all of their brains are being imported from the save brain. Beautiful sight. Now our loading, saving, everything is working. Perfect. Let's up the time to 20 and just let it play out a little bit, and let's see if we get some like really complex brain. Oh, another thing. One issue that's going to be happening right now is if we go to the neat network, no, if we go to the neat genetic manager, right here, where we have the starting save networks, we need to set found. Right now that's not going to be an issue, but for right now, set start. What was that bool? What did we save it as? Spawn from save. So right here in the starting save networks, we're going to do spawn from save equals false. So it'll be true starting off, but then after we spawn them initially, we set it to false. Just so it doesn't impact anything. It will it's going to be a problem in the future. Right now it's not. So let's do that, and let's speed this up to, let's say, 40, and let's see how it looks after a little while. This one seems pretty good. He's actually getting some food. And there we go. Now we're getting some more complex behavior, more than just spinning in circles. I'm waiting for a generation with a very different type of creature. something that maybe goes up, down, left, right instead of spinning in circles. Alright, this one seems to be really good. So we're going to go to 1, and we're going to let this generation finish. We'll go to 10. Actually, change the time to 10. Let this generation finish, and that'll save it, and then we'll spawn it. And this guy does not want to die. Perfect. So that guy should have been saved now. And then when we press play, we should have a group of very intelligent creatures. I guess not. The thing with this is a lot of these guys are impacted by each other. Like another creature taking the food that they're aiming towards. So yeah, this guy is the same guy that we saw before doing the really fast spinning and collecting foods, but with a little mutation. Each generation they're mutating more and more. So our saving and loading is working. That's perfect. Now let's get it to work. Let's get it to work kind of in a more automated, better way. We don't need to save every generation. We need to actually save based on the which generation is doing the best, and that is defined by how fast a generation is, like an agent, how long he's able to survive. Alright, so the way we do this, up on top now, we have our spawn from. We're going to create another public, but this is going to be an int. We're going to call this best time. And this is we're going to set this to be 100 to start off with. And then we're going to create another public int, add to best, and this is going to be 50. So every time the best time is hit, which is 100, 50 will be added to it, creating the new best time for the next generation. Okay? And now I'm just trying to see the exact way I did it in my code here. So the way we're going to do it, the thing is, our time is being stored within each fish controller. each time of how long a fish is surviving is in this controller, right? So we want the best time to be passed into each one of these the fish controllers, and then we want anytime it passes that time, we want the fish to die and save. So within our fish controller, we're going to create a variable called it's going to be a private variable, but we're going to serialize the field to make it visible in the editor. Private int best time for now equal it to 0, because the best time will be set for each fish. Right, so in the fish controller we have our best time, and whenever we we're going to create a new function in this called a wait function. This function fires after everything is loaded up. So within your fish controller, create an awake function, and in this we're going to set the best time. So best time equals game object dot find object of type, and we want to find the G manager, which is what contains our best time. So that will be 100, and then when it hits 100, 150, and so on. Right. Now that that's done, now when the death function fires in here, now we want to see when this fish is over the best time. So when we calculate the fitness, we'll do this in the fitness function. So this is also where death is called. So that's why we're also going to do this in here. If the time since let's see where my current time is. I don't have my current time set up in here. That's not good. Then is it even worth? Yeah. Okay, so we're going to create another variable here called current time since start. Right? And that will be basically how long this fish has survived. So this will be a same thing as this. And this will be a private float survive time. So you start off with 0. And then we update it in the fixed update. So this is going to be added. So survive time plus equals time dot delta time. So that's what updates it every step. Save your genetic manager file as well. Okay, but the fish controller. Survival time is updated, and then so actually an interesting thing is this is the opposite of our energy. Our current energy is subtracted by time to delta time, and our survival time goes up as you survive longer and longer. Now that our survival time is going up, we can go back to our if statement that we were writing in our calculate fitness function, and we can do if survival time is greater than or equal to best time, then we can save our network and kill the fish. So that will be right here. We'll print save fish. So we'll save the brain of the fish, and then game object dot find object of type. We'll look at the neat g manager. We're going to call the function that the best fish has been found. And we save it. And I believe it should be my network. So we're going to save the genome that's inside the network. So my network dot get my network dot my genome right here. Perfect. That saves the network, and then death. Perfect. And now we need to write this function, the best found function, in our genetic manager. Yep. So for that, we're going to write the function. We'll write it. We'll write it right here. And that will be a public void best found. Perfect. And you can put that function wherever you want it, obviously. Well, not wherever, but within the class. Now that this is done, so this is going to be an interesting thing. When we do the found best, we call it best found, right? We're simply saying that the best found network, well, we're saying that we want to now, the next generation, we want them all to spawn from this, well, not all of them, but we want some of them to spawn from this saved network. Now this way, the way we're doing it this way is, so whenever the best time is found, the next generation, the top 3 will be of the saved network. And that way we'll be able to explore more combinations of more mutations of a working network. So we know this network is doing good. Now we want it to mutate to do better, right? This is a lot better than starting from scratch every time from a network. Because if you're already close to solving the problem, why would you start over from the bottom? The only benefit you get from starting over from the bottom is if your top is stuck in like a local minima or something where it no longer can train better, but there is a better solution out there. That's when you want to have people starting from the bottom and finding a new path to the solution. So you want to have a mix of both. You want to have a mix of networks that are well trained and you already know are doing good, but you also want to have some people who seem like they're not solving the problem, who might in the future find a better solution. All right. So this will be spawn from save equals true. So now our spawn from save will be true. But this doesn't do anything for us when we're repopulating. Our spawn from best only really takes effect in the start function, right? So now we have to set it up to work in the repopulation function. So find your repopulation function. Mine is right here. And now we're going to set this up properly. I just want to see what's going on with this repopping. Okay. So we don't have to mess with that. Perfect. So now in this, we're going to do an if statement. If found best, well, if spawn from save equals true, else, there we go, right? Now that this happens, we want to first of all, we don't need to sort the population anymore. So what we're going to do is copy over these two right here and throw them into this. Right, and this is a simplified version. And then we are going to, first of all, since we do spawn from save is true, we have to add to the best time. So best time equals best time plus add to best. So add 50, add 50. And then this is start new population networks. Well, we'll get to that. So this starts each of our new population, but since we have a save that is really good, we can start the new population from that save. So our new population will be the same function, start with the same function we wrote, starting saved networks. Starting saved network. So now every time we hit spawn, whenever this is set to true, the network will be saved, and now all the next generation will be spawned from that saved network. And this isn't exactly we want to do it. We want to have some of them start from the saved network, some of them not, but for right now this is good enough. So we're going to press play here and just kind of see how this is going. All right. So now we will go into our, let's see the errors. What? 4163. Dot best time. Okay. $29,636. This right here, and that I believe is because of an import. Yep. So for that, we were using system. I wonder why. Let me try this real quick. I'm gonna change this to public and leave that. This is all monolith. Shouldn't be any error. What? How is serialized field not being found? Maybe it is an import issue. So instead of that, we'll do system dot. But this was working fine in our genetic manager class, which is using same import, same mono behavior, the strangeness. Only difference is that okay. I guess I'm just going to make this public. I don't understand why that's an issue, but I don't really want to spend a lot of time fixing that right now. Okay, so genetic manager, go down. We're going to change spawn from save back to off. Press play. And now they're all normal. You see, some of them are dead, some of them have 1, 2 connections. This goes to 50. Oh, okay. Another thing now we're gonna have to change is go to your script, go to your neat genetic manager, and go down to where you're sorting the population. Right here, and we can remove this save. We no longer need that. changing the time to 20, and we'll see. Our best time is still 100. Let's see if something makes it past 100. Yeah, alright, somebody made it to 100. So now we have a saved fish. And somebody just made it to, well, we're at 250. And each time you see a lot of these fish are spawning, whenever it's hit, they're spawning with same behavior. That's what we're looking for. And because it proves that the networks are being loaded from the same network. You see how they all kind of did the same thing in the beginning? But since they're competing with each other, they're dying off. They're going for the same food, and some of them are getting it, some of them aren't. They have to learn to live with each other as well. And that is the sort of behavior we're starting to see. You see how the big one was eating all the food that the little one couldn't get to. And now we see that none of them are actually able to make it past 450. Alright, finally somebody hit 500. Now he hit 550. And it was the same brain actually. So I'm going to let this run a little bit until at least we hit maybe 1,000. You guys can forward. And then we'll spawn from best to see if our first generation is able to survive for a long amount of time. Now look at that. These guys are good. $850, making good time. Oh, they're stuck. That's unfortunate. This guy seems pretty good. Alright, we hit 1,000. So now we're going to stop the simulation. We're going to put spawn from best to be true, and we'll save the time to be 1, and these guys should survive for a ridiculous long amount of time. At least 1 or 2. And if you guys notice, there's a lot of wasted energy. So we can mess with the fitness function to make it to where energy is properly saved and all that. Oh, they're going to stop at 100. Okay, let me stop this. Since our best time is 100, they're all going to die at 100. Let's change it to 1,000 because that's the best time that they made it at. And now let's press play. Let's press play. I'm going to speed it up to 20. And you see, these guys are like pretty good brains. Like you have 3 or 4 that were doing really good for a good extended period of time, and we still have 3 that are going. These are clearly brains that were loaded and saved from the best network. And yeah, I think that's basically, we're done here. Our loading and our saving is working. Our networks are starting from the best population when we have found best to be, where we have the spawn from save to be true. Yeah, this is perfect. I'm sorry this one took so long, guys. We fixed some issues that we had earlier. Now our the way that our fitness is happening is actually storing proper fitness values, and in the future we might even be able to change the way our fitness is doing to take into account how long a agent survives. So maybe fitness based on survival length is better, because our whole goal in this problem is to get agents that survive for the longest time. So agents that survive longer should get rewarded, right? So we could add that to the fitness function, add reward for how long you survived, how fast you capture food, all this stuff to get true chasing behavior, everything. So this is just cool stuff. I just wanted you guys to see that, you know, saving and loading is not that hard at all. The problem was some of the debugging we had to do, and that's always the issue in coding, is there's so much time you spend debugging. But the end is always a beautiful end, and I think this is pretty beautiful right now. And the next thing we're going to do is speciation. Either speciation or being able to actually click an agent and view their brains. Alright, you guys, hope you guys watched through this. I hope you guys learned something and hope it was interesting. If you guys liked it, please comment, subscribe, all that. Again, the only reason I continued this series is because I got very good comments. So I will continue to make videos that you guys want to see if I see good engagement and good user engagement. So, appreciate you guys. Take it easy. And I'll just let this play, but I'm out of here. Peace.